Hello guys, welcome to the reinforcement learning series, and in this video we will be studying about value iteration method. So let's begin. The whole part of the reinforcement learning is built around the value and how to approximate it. And we have defined the value as an expected total reward that optionally discounted, that is obtainable from the state. In a formal way, the value of the state is, we can write it as, okay, from initial state to whatever the next state to, and discounted. Okay, so this is the value of state, where this RT is the local reward obtained at step T of the episode, and the total reward could be discounted with gamma or not, and it's up to us how to define it. So in the undiscounted case, it corresponds to gamma is equal to 1, and the value is always calculated in some policy that our agent follows. And let's consider a very simple environment in three states, and that is, we'll take it as S1, and from here to S2, and from here one more as S3. Okay, one is going here like this, oops, it remain like this, and one here. Okay, so here we say reward is 2, and here the reward is 1, and they both are terminal states, so these are ends, and this is the starting point. So basically, uh, this is the agent's initial state, and the final state that agent is in after execution action, right, like from here, from the initial state the reward obtained from this is 1 as written over here, and the final state that the agent is in after action down, that is into this state, the reward obtained from this is 2. And the environment is always deterministic. Every action succeeds, and we always start from state 1. Once we reach either state 2 or state 3, the episode ends. Now the question is, what's the value of state 1? See, this question is meaningless without information about our agent's behavior, or in other words, we can say that it's policy. Even in the simple environment, our agent can have an infinite amount of behaviors, each of which we will have its own value for state 1. So let's consider one more example. Okay, so here we have an example from right. We will go to S is equal to state 2 end, and this is the starting one, and one is down, this is S3, and then is final S4. Here the reward is going to be minus 20, here it is going to be 2, and here the reward is going to be 1. Okay, so basically agent goes right with a probability of 0.5 and down with a probability of 0.5, and agent go right in 10% of cases, and in 90% of cases executes the down action. And we will calculate of the policies of basically we're going to calculate the value of all the preceding policies, and the value of state 1 in the case of agent going always right is 1, and for the always down agent the value of state 1 is 2. For the 50% right and 50% down probability agent, the value is 1 into 0 0.5 for right, and 2 reward for going down with a probability of 0 0.5. Oops. So it is going to be 1.5. And for the 10% right and 90% down, agent will be 10%, and this is going to multiply. Okay, now add, going down 90% probability, so it is going to be 1.9. Now another question: what's the optimal policy for this agent? And the goal of reinforcement learning is to get as much total reward as possible. For this one step environment, the total reward is equal to the value of state 1, which obviously is at the maximum at policy 2. Unfortunately, such simple environment with an obvious optimal policy are not that interesting in practice. For interesting environment, the optimal policies are much harder to formulate, and it's even harder to prove their optimality. So don't worry, we are moving toward the point when we will be able to make computers learn the optimal behavior on their own. And from this example, you may have a false impression that we should always take the action with the highest reward. In general, it's not that simple. And to demonstrate this, we are going to extend our preceding environment with yet another state that is reasonable, and that's why we have introduced this state 3 and state 4, and state 4 specifically with a bad reward of minus 20. And once we have chosen down the from the action state in 1, this bad reward is unavoidable, as from state 3 we have only one exit to so it's a trap for the agent, which has decided that being greedy is a good strategy. So with that addition, our values for state 1b will be calculated in this way, like the agent always going right, it is going to be, okay, let's make a small box over here. Yeah, for always right, it is going to be always right, it is going to be 1. The value of like always down, it is going to be 2. Plus minus 20, so it is going to be minus 18. And the 50% agent gets the 50% policy, and like this one. So in this case, 50% for this one plus 50% for the down. It's 2 plus minus 20. Okay, so this is going to be minus 8.5, and the 10% and the 90% case that we discussed before. So these things are already discussed before, so we just write it in this specific way. So it is going to be 0.1 for right, reward was 1, and 90% for going down. Okay, so this is multiply, this is also multiply. Okay, this is the same thing. It is going to be 2 plus minus 20 again, and this is going to be this is less space, guys. Okay, so minus 16 I'm writing over here. So the best policy for this new environment is now policy 1, so always go right. And the Bellman equation of optimality, imagine that our agent observe state. So let's make a new diagram for that. All right. So let's make it. Okay. Initial state. One is here, 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 and one here. And S1, S2, S3, S4. Okay. R3, R4, V1, V2, V3 and V4 by taking action 1, action 2, action 3 and action 4. Okay. So the Bellman equation of optimality. So you can imagine that our agent observes state S0 and has n available actions. Every action lead to another state S1 to Sn, and here we have 3 or 4 state. Just consider in the specific way with the respective reward of R1, R2, R3 to Rn, and also assume that we know the values, that is the vi of all the states connected to state S0, and what will be the best course of action that the agent can take in such a state. So if we choose the concrete action and calculate the value given to this action, then the value will be like this. Okay. Okay. And so to choose the best possible action, the agent needs to calculate the resulting values for every action and choose the maximum possible outcome. So in other words, it could be written as so if we are using the discount factor gamma, we need to multiply the value of next state by gamma. So we can also write it in this specific way. Okay, let's make a little distinction so don't get mixed. Yeah. So max and 1 to n and RA plus discounted factor with VA. Okay, fine. This may look very similar to our greedy example from the previous section, and in fact it is. However, there is one difference. When we act greedily, we do not only look at immediate reward for the action, but at the immediate reward plus the long-term value of the state. So Bellman proved that with that extension, our behavior will get the best possible outcome. In other words, it will be optimal. So the preceding equation is called the Bellman equation of value. So it's not a very complicated to extend this idea for stochastic case when our action have the chance of ending up in different states. When what we need to do is calculate the expected value for every action, and instead of just taking the value of next state, let's consider one single action. So I would make a separate diagram for that. So this was part 1, value iteration method at Q Learning. For second part, link is in the description. So please go and watch it. Thank you for watching the video.